Hello बच्चों, today we are going to start a new lecture of electrostatics in which we will solve some exemplar problems of NCERT. First example is example number 1.2. If a body gives out 10 to the power 9 electrons per second, how much time is required to get a total charge of 1 coulomb on it? In this question, it is saying that a body is giving out 10 to the power 9 electrons per second, and we have to calculate the time in which it will get a total charge of 1 coulomb. So in solution it is given that n is equal to 10 to the power 9 electrons per second and the total charge required by the body is Q is equal to 1 coulomb. Now let us consider that a small q amount of charge is given per second by the body. Therefore, using quantization of charge, we can write Q is equal to N into E, where E is the charge on an electron. So by putting the values of N and E, we get Q is equal to 1.6 into 10 to the power minus 10 coulomb. Now, using unitary method, we can find out the time taken, as time taken to give Q charge is equal to 1 second. Therefore, the time taken to give 1 coulomb charge is equal to 1 upon Q. From here we can get T is equal to 6.25 into 10 to the power 9 second. Therefore, we can say that the time is required to get a total charge of 1 coulomb on the body is 6.25 into 10 to the power 9 second. You also calculate this value in years. Next example is example number 1.3, which is how much positive and negative charge is there in a cup of water. Here we have to calculate the total amount of charge in a cup of water in this question. So for that, let us consider a cup contains 250 centimeter cube of water in it. So as we know that mass of 250 cc of water is equal to 250 gram, and the molecular weight of water, that is molecular weight of H2O, is equal to 18 gram. Now we can calculate the number of molecules in 250 gram of water, as we know that the number of molecules in 18 gram of water is equal to Avogadro number, which is 6.023 into 10 to the power 23. Therefore, we can write the number of molecules in 250 gram of water is equal to 6.023 into 10 to the power 23 into 250. As each molecule of water contains 10 electrons, therefore total number of electrons is equal to 10 into the number of molecules in 250 gram of water, which is equal to 8.365 into 10 to the power 25. Now we can calculate the total charge in a cup of water using quantization of charge, which is Q is equal to N into E. Here E is the charge on an electron. By putting the value of N and E in the equation, we get Q is equal to 1.338 into 10 to the power 7 coulomb. Next example is example number 1.4. It says that Coulomb's law for electrostatic force between 2 point charges and Newton's law of gravitation force between two stationary point masses, both have inverse square dependence on the distance between the charges or masses. Part A. Compare the strength of these forces by determining the ratio of their magnitudes. First, for an electron and a proton. Second, for two protons. B. Estimate the accelerations of electron and proton due to electrical force of their mutual attraction when they are 1 angstrom apart. Mass of proton and mass of electron is given in the question. In this question, we have to calculate the ratio of magnitude of the electrostatic force to the magnitude of gravitational force for an electron and a proton, and also for two protons. And in second part, we have to calculate the acceleration of electron and acceleration of proton due to electrical force acting between them. In this question, it is given that the mass of electron is 9.1 into 10 to the power minus 31 kilogram and mass of proton is equal to 1.67 into 10 to the power minus 27 kilogram. And we know that the charge of electron is equal to minus 1.67 into 10 to the power minus 19 coulomb, and charge of proton is same as the charge of electron. And the electrostatic force is given by 1 by 4 pi epsilon naught q1 q2 by r square, and the gravitational force is given by g into m1 m2 upon r square. Now we know the expression for electrostatic force, which is 1 by 4 pi epsilon naught q1 q2 upon r square. By putting the value of charges, we can get QE QP upon r square here. And the gravitational force Fg is equal to GME MP upon r square. To find out the ratio, we will have to divide these two. So we get the expression Fe upon Fg is equal to 1 by 4 pi epsilon naught QE QP upon GME MP. By putting all the numerical values of these, we get the ratio 2.27 into 10 to the power 39, which is the ratio between the electrostatic force and the gravitational force for an electron and a proton. And in second part, we can also calculate the ratio of the same forces for two protons. As we can see from the answer that the ratio of forces between an electron and a proton is greater than the ratio of forces between two protons. To find out the value of acceleration of electron and proton due to electrostatic force acting between them, we will firstly find out the value of electrostatic force between electron and proton. So by using the expression of Coulomb's law, we can write F is equal to 1 by 4 pi epsilon naught QE QP upon r square. By putting all the values, we get the numerical value of electrostatic force 2.304 into 10 to the power minus 8 Newton. Now we know that electron and proton has opposite charges, therefore they were attracting each other. So due to electrostatic force, there will be acceleration in both, and we know that the force of electrostatic can also be represented as m into a from Newton's second law. So from this equation we can write the expression of acceleration as F by m, and that for electron AE is equal to F by m. By putting values, we get the numerical value of acceleration of electron, which is equal to 2.5 into 10 to the power 22 meter per second. And by using the same formula, we get the acceleration of proton, which is equal to 1.4 into 10 to the power 19 meter per second. From here we can see that the acceleration of electron is greater than the acceleration of proton. Next example 1.5. In this example it is saying that three charges of same magnitude and charge Q1, Q2, Q3 are placed at the vertices of an equilateral triangle having length L, and another charge Q having same sign is placed at the centroid of the triangle. And in this question we have to calculate the force on charge placed at the centroid due to other three charges. So in the solution of the question, we can see in the figure, we don't know the value of distance between any of the two charges. So for that we will calculate the distance between the charge situated at centroid and the other charges, which is OA, OB and OC. So in triangle ACD, cos 30 degrees is equal to AD by AC. From here we can calculate the value of AD, which is equal to L into root 3 by 2. As we know that the centroid of the triangle divides meridian in the ratio of 2:1. Therefore we can write OA is equal to 2 by 3 AD. From here we get the value of AO is equal to L by root 3. Similarly, we can find out the values of BO and CO, which are equal and equal to L by root 3. Now the force on Q at O due to Q at A is given by F1 is equal to 1 by 4 pi epsilon naught Q square by L by root 3 whole square. Here the direction of force F1 will be from A to O. Similarly, we can write the force for other two combinations of charges F2 and F3, and we can see the magnitude of all the forces are same. Now using the vector law of addition, parallelogram law, to find out the resultant of F2 and F3, we get F is equal to under root F2 square plus F3 square plus 2 F2 F3 cos 120 degree, where cos 120 degree is the angle between F2 and F3. As magnitude of F2 and F3 are equal, so by putting the value we get F is equal to F2. Hence the resultant F is equal to and opposite to F1. So the net force on charge Q situated at centroid of the equilateral triangle is equal to 0. Next example is 1.8. An electron falls through a distance of 1.5 centimeter in a uniform electric field of magnitude 2 into 10 to the power 4 Newton per Coulomb. Now the direction of the field is reversed, keeping the magnitude unchanged, and a proton falls through the same distance. Compute the time of fall in each case, neglecting gravity. In this question, it is given that there is a uniform electric field and an electron is falling in it at a distance 1.5 centimeter. That is, electron falls in electric field and covers the distance 1.5 centimeter. After that, the field is reversed and in place of electron there is a proton falling same distance in it. Here the effect of gravity is being neglected. So in this question we have to calculate the time of fall in each case, in case of electron as well as for proton. In solution it is given that the distance traveled by each particle is 1.5 centimeter, which is 1.5 into 10 to the power minus 2 meter. The initial velocity is 0 since the two particles are falling. So initial velocity is 0. No force is acting initially. So the velocity, or we can say that it is falling from rest. The electric field intensity is 2 into 10 to the power 4 Newton per Coulomb. And we know that the electron and the proton has masses 9.1 into 10 to the power minus 31 kilogram and 1.6 into 10 to the power minus 27 kilogram respectively. Also, we know that the charge on an electron or proton is equal to 1.6 into 10 to the power minus 19 coulomb. The description of the question is shown in figure. Let us consider the time of fall of electron is Te and time of fall of proton is Tp, and the acceleration is a. Now we can write the formula of force. F is equal to Q into E, and also using Newton's second law, F is equal to M into A. Equating these two equations, we get Ma is equal to Q into E. From here we can get the acceleration A is equal to QE by M. This equation shows that acceleration is depending on the magnitude of mass of the two particles, because charges of the two particles are same and electric field is also constant, so it is only depending on the mass of the two particles and inversely proportional to. From here we can say that the acceleration of proton will be less than the acceleration of electron because the mass of proton is greater than the mass of electron. As two particles move same distance s, so we can use the second equation of motion, which is S is equal to ut plus half at square. From this, by putting the value of acceleration, we get time is equal to under root 2sm by qe. So from previous equation, we can write time taken to fall of electron Te is equal to under root 2sme upon qe. By putting all the values and calculating, we get the time taken is 2.927 into 10 to the power minus 19 coulomb. And in similar way, we can find out the time taken of fall of proton, which is 1.252 into 10 to the power minus 7 coulomb. Here time taken for proton is greater than the time taken for electron because heavier mass will fall faster, as the mass of proton is greater than the mass of electron. Therefore, it will have greater acceleration, as I have explained in last slide. And the second part of the question is asking if the particles are falling under gravity, what will be the effect on time of the two particles? There will be no effect on the time taken by the two particles because gravity doesn't depend on the mass of the falling body. Example 1.11. The electric field components in the following figure are Ex is equal to alpha x to the power 1 by 2, Ey and Ez are 0, in which alpha is equal to 800 Newton per Coulomb meter to the power half. Calculate first the electric flux through the cube and second the charge within the cube, assuming A is equal to 0.1 meter. Here in the question it is given that there is a cube of side A placed at a distance apart from the origin, and the electric field is towards the positive x direction, and the magnitude is alpha x to the power half, and there is no field along y and z axis. The area vector of right face and left face of the cube is given in the figure, perpendicular to the face and outward. So in first part we can write the electric field at left face EL is equal to 800 a to the power half by using the formula which is given in the question, Ex is equal to alpha x to the power half. Here we have put x is equal to a because the distance of the left face from the origin is a, and the electric field at right face of the cube is 800 into 2a to the power half. Here x is equal to 2a because the right face is at 2a distance apart from the origin. Now we can write the flux through left face is EL dot delta A, which is 800 into a to the power half delta A cos 180 degree. Here delta A is the area vector of left face, and the angle between area vector and electric field is 180 degree because the direction of electric field is along positive x direction and the direction of area vector is along negative x direction as shown in figure. Similarly, we can write the flux at right face is equal to 800 2a to the power half into delta A. Here the angle between electric field and area vector is 0 degree because the both are in positive x direction. Now the total flux through the cube can be written as phi L plus phi R. By putting the values of both, we get the total flux through the cube phi is equal to 800 a to the power half minus 1 plus root 2 delta A. From figure, A is equal to 0.1 meter and delta A is the area of the face of the cube, which is A square or 0.1 whole square meter square. By putting these two values, we get flux phi is equal to 1.05 Newton meter square per coulomb, which is the answer of part A. In second part, we will use Gauss law to find out the total charge enclosed by the cube. According to Gauss law, phi is equal to q by epsilon naught or q is equal to phi epsilon naught. By putting the value of phi and epsilon naught, we get the total charge q is equal to 9.27 into 10 to the power minus 12 coulomb, which is the answer of part B. Next example is 1.13. An early model of an atom considered it to have a positively charged point nucleus of charge Ze surrounded by a uniform density of negative charge up to a radius r. The atom as a whole is neutral. For this model, what is the electric field at a distance r from the nucleus? In this question, it is saying that the model of atom is like point charge nucleus having charge plus Ze, which is surrounded by the uniform density of negative charge up to radius r. That is, the negative charge are spread up to radius r around the nucleus. Here it is given that the total charge of the atom is neutral in this question we have to find out the electric field at some distance r from the nucleus. So in the solution of the question there arises three cases. First is the distance r is less than the radius of the atom. Second is the distance r is greater than the radius of atom. Third is both are equal. In first case, which is r is less than radius, let us draw the Gaussian surface at a distance r around the nucleus through point S. We can write the volume of that sphere V dash is equal to 4 by 3 pi r cube. To calculate the electric field at a distance r, we will have to find out the total charge through this Gaussian surface. Now, if rho is the volume charge density of negative charge over the sphere or Gaussian surface inside the Gaussian surface, the total negative charge Q is minus Ze and V volume of the whole sphere or atom is 4 by 3 pi capital R cube. Here we have taken Q is equal to minus Ze because it is given in the question that the positive charge is equal to the negative charge. So according to the charge distribution we can write rho is equal to Q by V. By putting the values we get rho is equal to minus Ze by 4 pi r cube by 3. This is equation number 2. As per definition of the charge density, which says that charge per unit volume is the charge density. So we can write per unit volume contains charge rho. Therefore, V dash volume contains charge V dash into rho. So let that charge is Q. By putting all the values from equation 1 and 2, we get the value of charge there is equal to minus Ze small r cube upon capital R cube. Now total charge enclosed by the Gaussian surface is equal to the sum of charge on nucleus and the negative charge present inside the sphere, that is present inside the Gaussian surface, which we have drawn in figure. By adding these two we get the total charge enclosed by the Gaussian surface Q dash is equal to Ze 1 minus r cube by capital R cube. Therefore, the electric field through the Gaussian surface which we have considered is equal to 1 by 4 pi epsilon naught Q dash by R square. By putting the value of Q dash, we get the result of this problem. In second part, which is small r is greater than r, we will draw a Gaussian surface through point P at a distance r. In this case, the total flux will be equal to 0 because it is given that in question the whole atom is neutral. That is, if we draw a Gaussian surface outside the atom, then the charge enclosed will be 0 for neutral atom. So the electric field will also be 0. This happened in third case also. Your homework is you have to solve the examples 1.1, 1.6, 1.7, 1.9, 1.10 and 1.12 and solve the questions which I have noted here. All these questions are based on the examples which we have understand in this lecture. Some hints are given here also for question number 24, 33 and 34. Thank you.